Hello everyone. Today we're going to be taking absolute value functions. You've watched the introductory video to absolute value functions. As you may know, the absolute value um, of a number or a variable just simply measures the distance away from zero. It can be thought of as the magnitude of a number. The absolute value of a function restricts the range, the y values, from being negative. It is a function where the independent variable has absolute value bars around it. And you'll probably see it quite a bit. So it's these big strange bars around it. So that means absolute value. You may also know, or these may also appear in your science course or other topics as an indication of distance. Naturally, the zeros are an important element, and we will really get down to the zeros because the zeros are very important because that's where a function can go from positive to negative or negative to positive. Now remember, absolute value restricts a function from being negative. So in mathematical notation, we often write absolute value functions as a piecewise function. Now this bit of notation looks a little bit daunting, but it says f of x is equal to f of x for all x where f of x is positive, and it's going to be equal to negative f of x for all x where f of x is negative. Now allow me to decipher possibly what this means. F of x is going to be equal to f of x. So the function will remain the same for all the x values where the y's are positive. And it's going to be negative f of x, or it's going to be the negative f of x for all x values where f of x is negative. And let me restate that second one. It is going to be the reflection of f of x where the graph is negative. So really what we'll notice is here, this is a descriptor of the function, this part here. And here, what we're really talking about for all x, this is going to be very closely related to domain. Okay? So we call this a piecewise function. So, for example, we are going to graph y is equal to the absolute value of x plus 3. So, and then we're going to write it as a piecewise function. Oh, my bad here. Graph. I should say sketch the graph. So I'm just going to graph that here, and I'm just going to make a quick sketch of this. So here we are. Here's my Cartesian plane, my xy plane, right? No big deal. I'm going to start off by graphing y is equal to x plus 3. What we're able to see is that we have, if you notice, I just dropped the absolute value bars. So I know that we have a y-intercept of 3 and an x-intercept of negative 3. Now you can find that out by equating y is equal to 0 and solving for x. So here is what that function looks like. And when I say that function, I mean this function. Y is equal to x plus 3. And very simply, if we want to graph the absolute value of that function, I think I'm getting excited, moving the paper around a bit here. Wherever y is positive, we keep y as positive. So if you notice, f of x was positive in the green section, so it remains so. Now if you notice, over here, my graph is negative. Now since I'm just sketching the graph, I need to take this portion of the graph and I need to reflect it about the x-axis. Now, you probably remember reflecting about the x-axis from a couple of times in this course. Really, all we're doing is we're multiplying the y values by -1. So the graph, the absolute value graph, will now look like this. So I'm going to write this as a piecewise function, and maybe this will help out. So I'm just going to say f of x, y, it doesn't really matter, y is equal to, I'm going to make these crazy set brackets. So y is equal to, or f of x is equal to, now it's this section here. Now I'm just going to say x plus 3. X plus 3, where x, actually we'll save this for later, but that describes this portion. But my graph was reflected only in this portion here. And what domain is a good descriptor of this part? It is where x is less than -3. Now, what is the descriptor of this part of the function? The descriptor of this part of the function is x plus 3. That's the graph, where x is greater than or equal to -3. So again, that negative means we reflected the original function. Wherever x was less than -3, the function remained the same. X plus 3 remained the same for all values that are x are greater than or equal to -3. All right, so, and by the way, that was sketch the graph. Didn't really graph it there. We're losing tons of points in terms of accuracy and stuff. So if you would like to do this next example, we're going to write this as a piecewise function. But just so you know, you have to have an incredible amount of knowledge to go from a absolute value function to a piecewise function. So typically where we need to go is we need to graph the original function. So I'm just going to drop the absolute value bars there. And I'm going to graph this. What do I know? I know, since this is a sketch, this is an upward opening parabola. In other words, it's upward opening, and I would like you to press pause and find the zeros of the function. Good. I'm glad you're joining me back again. You likely determined that your zeros are at -1 and -2. You can easily find this out simply by letting y is equal to 0, right? If we're finding our x-intercepts, we let y is equal to 0 and solve for x. Isn't it amazing? I just take some knowledge for granted now that we've been quite familiar with it. So that's what this function looks like. Now the absolute value function, I am going to write this in a little bit different way. Now I notice that I've been a little bit inconsistent in my notation, but since my function was y, really this should be y. So we always read functions from left to right. I'm going to continue doing that and make sure that I'm building my piecewise function here. So if I notice, my function is positive there. I'm going to start with the most left. So my absolute value function stays as x squared plus 3x plus 2. Where? I guess where x is less than -2. Now, do you see this middle section here? This, my function, is negative. So my y values are negative, so what must I do? I must reflect this portion of my graph upwards. So I'm just going to draw that in yellow. No specific reason. I should be doing it in the same color, but I want to exaggerate the point. The function was x squared plus 3x plus 2, but what did I do? That is that negative part in the middle. I simply reflected it. In what domain is this reflected? Well, it's reflected where x is between -2 and -1. Now I included these points. You could have included -2 in the above and it won't change anything. Last but not least, let's take care of that third arm, the one that we've been ignoring here. This third arm follows. It is recognized that my y values are positive. And we say our function is positive in that domain. So it remains as x squared plus 3x plus 2 for what domain? For every x value greater than -1.